Can I start?
Yeah, sure.
Okay. Yeah. Thank you very much for the invitation. I'm Xiaoying Zhuang from Leibniz University, Hanover. I'm the chair of Computational Science and Simulation Technology. I'm from Faculty of Mathematics and Physics. So just a little bit background about the university. Here's our logo. So it's actually the handwriting script from the mathematician Leibniz, if you know the calculus integration. So the left-hand side is the binary, and right-hand side is the decimal. And so that's actually his idea to have the binary mechanical machines.
Oh, really?
Yeah. And our university is named after the mathematician. So here is my group, and here's the main campus of the university. And there's Leibniz exhibition museum, and every last Friday each month there is a tour introducing the achievements and his life story about Leibniz, and also his mechanical machine calculator. And there's also his most descent curvature with Leibniz, where he proved that the fastest way of descending is not a straight line. And here's my group, quite international. We have group members from Vietnam, from Germany, from Italy, from Iran, and also from China. And Leibniz University is one of the technical universities. It's called TU9, Technical University 9. So the TU9 Association is from 1960s. If you're familiar with some other university in this 9 university associations, is Technical University of Munich and Aachen and TU Berlin. Yes, this mathematician, he lived and worked in Hanover. If you see his signature like this, you can see the L looks like the integration sign. And this is the Stapelbad, where he has a hobby to make mechanical machines. And one day he's inspired by eating from a friend from France. The French mathematician sent him this eating where he finds the dashed line and solid line. The combination of dashed line and solid line can represent yin and yang. And if you have 6 of these lines, you have 64 different combinations. And that's actually meaning binaries. The dashed line is 0 and solid line is 1. So, and he thinks he's inspired by the ancient graph. So about my background, I did my PhD in computational mechanics. So I'm always telling my students, even though I'm in mathematics and physics department, but my background is in mechanics. So I'm neither mathematician or physicist. So, and then I moved to Germany in 2015 with Sophia Sky Prize from Alexander Von Foundation, and I became professor in 2019. So I moved several countries from Shanghai to UK, and then to Norway, and then to Germany. I have an ongoing ERC study grant about the nano-energy harvester utilizing flexoelectricity and piezoelectricity for self-powered model implant. So I've so far graded 5 PhD students in Germany. This is the Chinese students, and we have the online defense in hybrid form. And this is my other PhD students who work on machine learning. So the isoparametric or parametric machine learning is actually from Ming. And yeah, if you know Pedro Arias, I don't know. Yeah.
Is that him? Oh my
Pedro
God.
Arias.
Wow, he read this shape.
Yeah, so he came to Hanover. And this is Professor Chen Li from Swansea University, also well known in computational mechanics.
Say.
Yeah. And I'm also supporting young researchers in my group. I'm hosting a Humboldt Fellow. If you're interested to apply for talent program or fellowship in Europe, there are 3 types of programs. The first one is the Humboldt Fellow from Alexander von Humboldt Foundation in Germany. The second one is Marie Curie Fellow, which is also prestigious from the European Union. And the third one is Newton Fellow from UK. So in my group, I have one Humboldt Fellow. He's coming from Beijing Institute of Technology, and he's working on a contact problem with thermal electromechanical field coupled together with a boundary element method isogeometric boundary element method. I'm hosting also Teresa Chen. She was originally from Australia and Queensland University of Science and Technology. And she's working on the tribal electricity energy harvester, where we can convert the muscle contraction and body movement energy stored into the capacitor through the tribal electricity. And her background is combined biomechanics, experiments, and simulation. And she actually got the highest scores, 98.8 of 2021, and she's in my group. So I changed my title today because I talked to Professor Lee that he would prefer the metamaterial topic more than the flexoelectric non-energy harvester. So I was modifying my slides. I want to give you some background. He said that so many people talk about metamaterial nowadays. It is true.
Sorry for extra.
Yeah, so many. But it's actually metamaterial is very wide umbrella word, and people talk about metamaterials in very different contexts, and they are meaning actually different things. If you talk to physicists about metamaterials, they are mainly focusing on the photonic, so electromagnetic wave manipulating, for example, cloaking materials. And that's very different from what we are talking about, mainly in mechanical civil engineering. That's mechanical metamaterials. And if you talk to people working condensed matter physics, and they're actually working on wave attenuation or phonons. So I'm really talking about elastic wave attenuation, that's phononic metamaterials. And some of the letters are in Chinese because some of them are presented before in a conference in China, and I want to translate it to make the audience understand better. For the mechanical metamaterials, folks know about it. There's auxetic metamaterials. That means the Poisson's ratio is negative. And that can be, it's actually a structural effect because there is no natural continuum material that has negative Poisson's ratio. The Poisson's ratio is always positive. When you have negative Poisson's ratio, auxetic effect is usually coming from the structural effect. So you design a spatial topology, and you have man-made artificial materials that shows unusual properties. So the auxetic materials, when you compress it, instead of expanding, it will shrink, and it will stretch it. Instead of shrinking, it will expand. So this is unusual properties as a result of the structural effect. So the other type is like you have zero shear modulus. So when you compress, it's kind of stiff, but when you give the shear loading, and there's no resistance, but it's actually also due to the structural effect. You have this hinge that has zero stiffness, and you have no rotation stiffness. So when you give the shear force, it's behaving like fluid. So we know that fluid is almost incompressible, and then it cannot resist shear force. So it is soft in shear loading. So there are many different fields that metamaterials can modulate: acoustic or elastic wave or heat, because the source of heat and elastic wave, they can both be classified as phonons, while the electromagnetic is belonging to the photons. And this is a review paper from Extreme Mechanics Letters Journal, where they gave a review of the different groups of materials, and they showed there's limitations in a bigger picture of different materials, like from graphene elastomers to ultralight metallic materials and so on. And the traditional materials, they have a parallel line for their limit for Young's modulus, and there are more graphs, more properties, like also for the tensile strengths and so on. So in fact, in many areas, the materials limit has been already exploited. So that's why engineers are trying to go beyond the current limit of materials by engineering materials to find new topology, new features through the materials engineering. And this is the case for mechanical metamaterials, like in this review paper. It is the same also for the semiconductor industry. There is the physical, non-physical rules like Moore's law. The Moore's law is not a physical rule, it's just a prediction for the growth of the density for the resistors in the chip, that every 10 years the cost will reduce and the intensity of the resistors in the chip will double. So the non-physical law govern this semiconductor industry has died out. There is stagnation in development around 2010, and the density of the chips resistors is like flattened out. So it's also going to the limit. And the silicon crystals, they have reached really to the manufacturing limit of 10 nanometers. So for mechanical metamaterials, my group, we are looking at the auxetic metamaterials and also the phononic metamaterials, including topological insulator. I give the assumption of this architecture structure because architecture structure was also one of the key area in the guideline from National Science Foundation in the US. They listed the key research areas in the future. And one of them is the architecture material. For example, you can design an auxetic cores in the middle so that you can program the failure processes. It can be used, for example, in the energy absorption and information control in different structures. You can also use it for the wave control or wave attenuation. There are many potential applications for metamaterials, for mechanical metamaterials, for different structures, for sensors. Also, you can enhance signals. You can amplify signals with substrate. And also there's lightweight structures, for example, metal foam, composite, and also energy harvesters. You can try to guide the wave in certain directions that you can maximize the energy efficiency for the energy harvesting. Also can be used for the machinery. Indeed, the metamaterial development is exploring the new metamaterials, or the title is incomplete, for the international trend. For civil engineering, there is also the common goal, and different big initiatives are undergoing in different countries, also in Germany. People want to explore new materials functions, and they want to reduce the materials, less materials, yeah. And also they want to have energy reductions as the international research trend. So you can see here is in Stuttgart, they have been working together with Max Planck Institute, where they want to have the digitalization industrial 4.0 to automate the lightweight structures. So they have these woven structures in the middle to reduce the material use and weight for non-load bearing, like you have lots of walls or separation structures in the building. They have a demonstration building, and so they also build some lightweight structures in Harvard campus using this new type of woven structures, which is manufactured by robots. So in 2019, Germany set up an excellence cluster for developing intelligent construction. And the first phase like 200 million, and it's extended further for another 7 years. So the excellence cluster in Germany is usually 7 years, another 7 years, and maximum 3 phases. So each phase is between 200 million to 400 million. Aachen, they also obtained digitalization in civil engineering and architecture for 400 million euros, and they started in 2020. And in the US department, they exploit metamaterials for different structures, and EU, Japan, they all have listed metamaterials and their future key development area. In this talk, I want to focus on the elastic wave attenuation, with special interest for geotechnical engineering for underground structures. And this is a picture for the underground structure complex in one of the big cities, Hangzhou in China, that's located in East China. So usually in city, we have really limited space for urban development for both background and underground. You have so little spaces between the metro line and underground facilities, parking places, and the buildings. And what happens is, when the low frequency wave is transmitting to the buildings, that can cause equipment long-term cyclic damage. For example, for the electric equipment, for the switches, the low frequency vibrations is unfavorable for the equipment reliability. And and for example, this is the equipment of atomic force microscope in Peking University. And then the metal line 4 is passing through the campus. And usually the normal function should be like this on the right-hand side. Whenever there's metal line passing by the building, and they have billions of high precision equipment that cannot be working. anymore because of the low frequency vibrations from metal line. And we know that the metal line vibrations usually between 60 to 100 hertz. So on the other hand, you know, the earthquake is even lower, 1 hertz or half hertz. Yeah. So, but they all belong to the elastic wave. So the traditional way to attenuate elastic wave is you open the trench. The traditional, like on fitting new materials, traditional way is having large volume, but it's really not effective in attenuating low frequency vibrations. They cannot be completely eliminated. So what would be the solution? As in last 20 years, people are looking at the metamaterials. That is actually the sculpture, and showing the nature of the sculpture in France. So what is metamaterials for phononic or for elastic attenuation? Metamaterial is an artificially constructed heterogeneous composite. So it's not natural materials in continuum form, but it is periodic small structures. For example, one unit cell. Usually the size of the typical one unit cell is much smaller than the wavelength cell. And then because of the wave interaction and also the backscattering, and wave can not pass through certain frequencies when you can design the structure in a careful way. So what can it be used? It can be used for attenuating elastic wave, but can also be used for magnetic optics and many other applications. So the magnetic and optic belongs to the photonic, and I'm focusing on phononic. Yeah. And usually the unit cell can be designed on demand, depends on the application background, what's the frequency range. Actually, people starting to look at it like in Switzerland or in Europe, there are many projects, and this is like from one paper. They do the size test by putting the periodic pillars, and these periodic pillars is pre-calculated, and they have a target frequency, they have certain geometry and materials combination, so that you can see there are different the source of vibrations here, and there is the accelerometer that is testing, and the wave can be successfully attenuated or blocked, which is from by the concrete barriers. So they have the size test, and people are using other ideas like they want to combine the forest and the trees as arrays, use this as a natural barriers for the wave. Actually, in my group, we also have carried out the layered soil wave attenuation test. So because we know the soil and the ground, they have different layers. And the question is, how can we utilize the different properties of the soil? You also have the groundwater, and you have viscosity, you have different Young's modulus, they have contrast of material properties. Can we design metamaterials according to the geological conditions and to achieve, for example, you can have the this band gap so that the wave cannot be transmitted, and at this frequencies the wave can be stopped. You can design it according to the geological conditions. So this is like the indoor test where we have the accelerator, signal generator, amplifier, and the accelerometer to test the effect of the wave attenuation. There's also gradient metamaterials for surface wave attenuation, so it's very active research direction internationally. And also metamaterials can block surface wave by trends. The traditional ways is you use the spring mass, the spring substrate for reducing the vibrations. Or recently, people also use the metamaterials around the foundations of trains for better performance for wave attenuation. So how does this work? As I mentioned, the metamaterials are of much smaller size compared to the input wave, and then through the band hybridization and also the wave interaction, you can actually generate a forbidden band gap frequency, so where the wave cannot transmit through. So you can also design the metamaterial in a special way. You can combine the two different unit cells so that the bulk of material is an insulator. No wave can pass it. at certain frequencies, but only at the interface the wave can go. It's called a topological insulator. So it's only conducting in the boundary, but it is insulating in the bulk material. So that is analog to the photonic metamaterials. You know, the quantum spin Hall effect, that it is only conducting at the edge, but not at the bulk. The photonic analog to the photonic is similar mechanism, but they are of different wave. So this is like what I mentioned. You can have a larger band gap. It's more than 100 Hertz frequencies when utilizing material parameters, utilizing layered soil. So I want to show some metastructures in soil, where this part we didn't consider the viscosity yet. Later on, I will show you how we consider viscosity. So this is the common material used in civil engineering. You can have rubber, aluminum, steel, concrete, and with special design, you can compute or test what is the band frequencies and band structures, what is the band gap for different type of materials. So you can also combine them to find new features, and engineers adjust it to locate the band gap just exactly in your target frequencies. For example, this is the concrete, and outside the soil, the second design is concrete plus the rubber. Yeah, because rubber has the damping effect. And the third design is we combine the first one and second one together. We have the concrete with rubber. Rubber is outside confining layer, and the concrete is the top pillar. And you can play around with the parameters of D2 and H2 that will change the band gap frequency range, and it also will change the band gap width. Yeah. So in this paper that we published in IJMS, that we combine these two together to, so that the performance is reaching our targeted goal. I want to introduce the concept of the unit cell, and this is the reciprocal space. Before we have the unit cell is in physical space. You have triangles, you have square, whatever, circular, and then you need to map this physical geometry into the reciprocal space. And this irreducible unit cell is mapped into the Brillouin zone. And then this wave is transmitted in the unit cell described by the wave vector. And wave vector, in this case, for example, is gamma, chi, x, chi, or m. And then this is wave vector in the kx and ky directions. So the unit cell width is the inversion of the Brillouin zone size in the reciprocal space. And then this is the wave vector showing the band structure where you have pillars as the first design. So we have relatively narrower, we have relatively higher frequencies. And then the second design is the concrete combined by the rubber. You have a little bit narrower band gap. Yeah. And then when we combine the two designs together and change the height and the thickness for the lower part and the upper part, we can locate the band gap in the lower frequencies, which is lower than 10 Hertz. It's between 5 to 10 Hertz because most of the wave in civil engineering is in the low frequency range. And then you can have both the wider band gap and low frequency ranges by trial and error. Of course, you can introduce machine learning by parametric study. We have also a paper on this. We can do the inverse design based on demand. It is different from Timo's talk, which is based on visiting bone neural network. It's purely data driven. You can train neural network to realize the inverse design. In this combined design, we can detect the wave vector change with respect to different frequencies and different mode. You have the DY, the X mode, and you also have the SH mode. So for the surface wave, for DY and the SH mode, they cannot be excited by the radial surface wave. These are dead mode, but nevertheless, they can appear in the band gaps that will reduce in the transmission of the wave. So that's very interesting. Yeah, and if we change the height of the pillars, And we will find that something more interesting is if we change the height of the pillars. So what we call the gradient metamaterials, and we can find that the incoming wave have antisymmetric properties when the excited wave from the left-hand side and right-hand side, they can be attenuated, but at different stopping pillars. For example, it's incoming wave from the left, so it will propagate few pillars, while the incoming wave is on the right and will stop at the third pillars. So here shows the contour plot of the elastic energy field. And if we break the symmetry of the materials, for example, if you have the same size, you have the direct point where you have the two modes degenerate together. So you have mode 1, mode 2, 3. And for example, here the modes 3 and 4, they have one degeneration point. And they meet at one point that is K in wave vector spectrum. And at this direct point, these 2 points, they meet together. And if you break the symmetry, you change the size of two neighboring cells. You will break the symmetry and generate the band gap. Yeah, and that is eigenmodes of two degenerated direct form. And then when we change the symmetry, you can have a band gap. In utilizing these properties, you can play with the size of the unit cell so that you can change the location of the forbidden band or band gap from higher to lower frequencies. And also you can change the size of the pillars. If the larger pillar is located interface, you have different higher frequencies. And when you have smaller pillars like here, SS, and then you have the lower frequencies at the interface. And the wave is only propagating at the interface, and above is the insulating. And then here is simulation that can be done in console if you're familiar with it. So here's the exciting source, and we have, as I said, we break the symmetry. You have different sides of unit cell. One is alpha 1, the other one is alpha 2. You can also invert it. And then you can see when there's exciting source, no matter how you place these two phases of materials, the wave is only propagating at the interface, and the bulk of the material is insulating. So that means if you have some structures you want to protect, you can design metamaterials as barriers so that when there's incoming wave, so the structure will be protected and the wave is only propagating along the interfaces. On the other hand, you can also harness energy, which is very interesting. You can put piezoelectric or flexoelectric. I don't know why it's like this. Low energy. I don't know. And you can put the energy harvester at the interface. As I mentioned, you have two cells, right? At the interface of two cells, the wave is propagating. And you can put the piezoelectric patches along the interfaces so that you can maximize energy harvesting efficiencies. From our test, you can put 70 or 80% of the energy when you put this energy harvest. Oh, you put the energy harvest along the interfaces. Yeah. And here you can see as one drawback is it's quite sensitive to the frequency range. When it is 10.5 hertz, we have the maximum power density, but it goes quite quickly with the change of frequencies. Ideally, you want to have wider frequency ranges. What you can do is you can combine different types of metamaterials together along the path. We also recently conducted studies on that to have a wider frequency metamaterials. Yeah. As I mentioned, metamaterials, you can design it for the interface mode by breaking one direct cone point. You can also have more stable, it's like defects immune topological insulator by designing the analog to the quantum spin Hall effect, where you have the full degeneracy direct cone point, because that will be generating the spin orbit coupling at the interface mode. So one way to do it is you can break the symmetry by introducing deformation. For example, the original unit cells, you have rubber or concrete, they are symmetric. And then if you change, like if you can increase the pressure or use other ways to change geometry, and you can reduce diameters of these unit cells, you can actually induce the space reverse symmetry, inversion symmetry, and by this way you can also design metamaterials. Actually, the topological insulator is not only used for the elastic wave, it can also be used for the other type of wave. Like you can tune it from a thermal wave, you can also tune it from electromechanical wave. For example, you put some piezo electrodes here, you can put electric field that you can also expand and change the topology for the cell. So this is like we designed the two inversion symmetry of the unit cells where we have a center source of the vibration. Yeah, and then we put actually defects along the pulses. And you can see the wave propagation still robustly goes through the interfaces and it's quite immune to the defects. We put like 2 or 3 unit cells lengths along the interface with defects. So it's immune to the back scattering and it's robustly propagating along the interface.
What's the size of the problem? Dimension size.
This size of the problem is centimeters, unit cells centimeters. And then you can see that we have many unit cells here. So it's like meters scale. Yeah. And the problem is when you change the unit cell size, when you reduce the size, it's softer for the high frequencies. When you want to go for the lower frequencies, you need to make it larger sizes. So that's also a common problem for civil engineering. You need to make bigger unit cells that waste lots of materials. So there's question is, can you design smaller unit cells as a barrier, but for lower frequencies? Yeah. This is the work we have done for the topological insulator with level set topology optimization. So the one I mentioned before has only one direct component for the degeneration. And if you want to have more robust topological insulator, you need to have 4-fold degeneration. That is the quantum spinning Hall-based topological insulator. This will need lots of education in the physics about what is quantum spinning Hall-based topological insulator. I need to talk another 45 minutes about it. So, but general idea is we want to use the level set method. Perhaps you know it. It's a topology optimization method to set up the objective function. For example, we want to first have 2-fold degeneracy at one point in the wave vector, and then we use topology optimization to generate 4-fold degeneracy at this second point. And then we want to open the band gap further, also with the topology optimization, but only changing the middle cell. And this unit cell, when you fold it outside, this is extension of this unit cell. You can see it. There's a zone folding theory for that. Yeah. And then the middle part is further topology optimized before it's this topology. And then you optimize it to open the band gap. So the objective function is to maximize the band gap. Yeah. And finally, is to have the maximized passing band. And so that when you put these unit cells together, they have the interface mode. So this is the procedure. So we have first objective function. J1 is to move the first mode down upwards, and the J2 is to move the second mode downwards. And the J3 is controlling to make the degeneration point so that J3 should be minimized so that the first and second mode, for example, it can be third or fourth mode, doesn't matter. So 2 modes, they can be minimized at one point and degenerated. Yeah. And then we use the level set, which is the Hamilton-Jacobi equation. This level set is a scalar function, and this is the velocity of the level set, which is driven by the sensitivity analysis for the Gamma equations, which is the wave propagation. And then this is the level set updating. We're actually using radio basis function. Yeah. So this is the objective function where we are optimizing the W with respect to alpha. Alpha as parameters from the radio basis level set method. So this is our initial geometry, and the final geometry is what you see before with this complex topology. Yeah. So this very interesting here. You can see this unit cell A and B. Yeah, they have the same band structure. But if you solve the eigenmode for the unit cell A and B to calculate the Berry curvature, they are exactly the antisymmetric. So this is the eigenmodes for A and this eigenmode for B. So they have the same band structure, but the opposite for the Berry curvature. So that is very interesting when you combine these two unit cells together. Yeah, and then you can have the supercell A and supercell B. This is a repetition of unit cell A, and this repetition of unit cell B. We call supercell. Yeah, the supercell, they have the same band gap and very similar, almost identical band structures. But when you tessellate AB, yeah, together, for example, here it's AB and AB, but they are chiral. Chiral means it's directional dependent. When you have the incoming wave, for example, when you have the incoming wave from one, and then because we have spin-off coupling, yeah, and then A is on, oh my God, A is on the right hand side of B, and then it can propagate.
Because you speak so fast.
I don't know what's the problem here. Right. Maybe I shouldn't use the pointer. So because one is propagating this way, and then it will not travel through. It only travels along the interface where A is on the right hand side of B. So this path A is on right hand side. It will go, and it will turn. It will stop at this interface because this path A is on the left hand side of B with respect to the wave direction. So that's very interesting. You don't get these properties when you only have two-mode degeneration. The two-mode degeneration is not quantum spinning. They don't have the spin orbit. It is only giving the interface properties, and it can go in both directions. Only the quantum spinning effect have the spin orbit coupling that it is chiral. The wave will stop at this interface to return. Yeah, that's very interesting. Okay, the other question is in civil engineering, it is not only the frequency that is important, it's also the energy. For example, you say, okay, you design metamaterial, you can stop the wave at certain frequencies, but when it is lots of energy, the metamaterial will be destroyed. And then the question is, can we design metamaterials not only working in the frequency that we are interested in, but also can absorb more energy? So the idea will be, can we combine the advantages of objective metamaterial that can absorb more energy, can go under more deformation, and combine to give the band structure, the wave attenuation properties of materials. So we are now trying this. So certain design, you can have both the band structures at, for example, low frequencies around 10 Hertz that can stop the transmission, can absorb most of the wave, but can also absorb the energy. Yeah. So the unit cell I mentioned before is we have, for example, object material, we have a unified topological optimization procedures both for 2D and 3D, and this paper is on CMME. So whatever auxetic properties you can give me, it can be anisotropic. You can have auxetic different Poisson's ratio in different directions. I can give you the topology that is matching your objective Poisson's ratio. So there's a final microstructure, and we can also do it for 3D. You can have the objective function for the elasticity tensor, yeah, where you have the objective Poisson's ratio in different directions, and you also can control the volume constraints. You have the governing equations, and this is the 3D one where we can give the final topology like this with anisotropic. I didn't use it on top. And the blue line shows we use the model order reduction. And this shows the different topologies where the level set is quite robust to evolve into anisotropic auxetic materials. And finally, you want to print these materials when you use the STL file where you don't have very smooth smooth description of the geometry, you use accuracies. So that's why we use IGA here. to keep its original curvature smoothness. One example is we imported the AutoCAD design file to the STL file for the 3D printer. Yeah, some models they just draw a straight line for where it should be curved. For example, the correct one, you have this rotation degrees, yeah, here, yeah. And then we import it into the 3D printer, they put all these straight lines. And then after you print it out, you actually realize it's not exact because of error in manufacturing. So there's also a problem with metamaterials. What you modeled and simulate in the computer is not finally what is performing. Because when you make it straight, you can see the rotation degrees of freedom is missing. But actually, that's the key for the structure effect when you want to obtain aesthetic properties. So I want to emphasize maybe in the future you need to have digital twin that is can observe where the source of error coming from and can correct the error in manufacturing, have a learning curve, and then can compensate it in your digital model because there's always error in manufacturing. There's also a recent paper from Xiaoying where he used the artificial intelligence for compensate the error in 3D printing because of the temperature, because of the particle size, and so on. This is very interesting. Yeah, the previous automated materials, I think I talked enough. All the metamaterials I showed before, we don't consider the viscosity. But you know, the soil, they are when they have water in there, they actually have the viscosity. So we know that you don't need to consider damping for steel, for aluminium, yeah, but not the case for soil. Concrete is okay, but for soil, you need to consider the viscosity. So we need to rederive the equations, considering complex parts. So the governing equations will consider not only the real part. Before all the band structures only consider the real part. You need to consider the real and imaginary part of the wave number because you have the energy loss. Yeah. So here, without going to all the masses, I show here's the wave governing equations. You have the imaginary part, and this is block theory where you look at the frequency domain. Yeah. And then here's the governing equations, and resolve these governing equations in terms of PDE. So it's actually quite easy for the PhD student to start with that. So here shows the effect of the viscosity. So when you have complex band structures, the transmission spectrum is very different from the pure the elastic without considering the viscosity. And in fact, when you're considering both the rubber viscosity and the soil viscosity, here's increased viscosity. Yeah. You can actually expand the larger range for the wave attenuation. So that's actually advantages when you want to design the metamaterials for surface wave attenuation. Now, recently, we are also doing indoor model test. So to verify our experimental results with shaker, signal generator, and power amplifier. And then we have quite agreement with experimental results and simulations. This part has not been published yet. Yeah. And finally, the last part is also very interesting. This working with physicists on a non-Hermitian metastructure. We know any system that exchanging the energy with the external world, it is a non-Hermitian system. So it's not ideal. So one question is, as I showed before, the incoming wave, when you have different conditions, the attenuation function is very different. Can we have a metastructure that is attenuating wave robustly, independent of the position of incoming wave? Yeah. So to realize this, one solution is to develop a non-Hermitian system that you consider the gain and loss of the system. You can have a pair of forces, like the left-hand side, and the opposite one is the loss one. So that is the gain one that has the leading to the negative imaginary part of the eigenfrequency, and the loss part is leading to the positive imaginary part of the eigenfrequencies. And so that you can have velocity dependent forces dependent on the input wave velocities. You can adjust the N2, N1, N2, and N3, and N4 as a pair. So that is showing when you're generating different pair of forces and you have different location of the forces like F and G and H, and you can have the similar attenuation functions that is independent of the excitation forces. Yeah. So having talking so much, I think metamaterials, is quite prospective. It can have also lots of applications for civil engineering, but it's still in the infant stage. Lots of tests are indoor. And for the substantial applications, there are many factors we didn't consider yet. That is heterogeneous of materials. Because the soil, they have a lot of heterogeneity. And you can also have inclusions and other particles. So this is not considered in the model. And also in the reality, the frequency sources is changing. So we are only targeting at small range of frequencies, but input source of frequencies like they can have wider range. So there's still a long way to go before it can be commercialized and used for practical applications. Yeah, thank you very much for your attention.
Question. By the way, I realized that you are so flexible.
Sorry?
You are so flexible for my request to change this.
Because I changed it quickly for you because some slides are with Chinese. I didn't complete yet. Yeah.
All right. Thanks a lot. Do you have any questions?
Great presentation, giving me a lot of ideas. Great.
Thank you. Okay.
No questions. Actually, I asked her this subject present because we have big issue regarding the sound transfer between different stories. So we have this is a big social problem. So people are talking about how to control the sound transfer between the different stories. But of course, the thickness of the slab is
only increasing this thickness is not helping. Yeah, you need to have special materials.
Yeah. That's why I asked you to provide some clue for such kind of solution.
And my colleague have actually patented. They reduce the noise in the big turbine. For the airplane, for big turbine by 20%. It's not that 20%. They tested in the western part of China. So they have very special topologies with aluminium. It is working. Yeah.
Another problem is they do not allow too much cost increase.
That's true because I talked to tunneling company.
Is your project in Shanghai? Is tunneling?
I'm doing experiments as I mentioned to you. I visited the tunnels. They have code. They don't like you change their railway. They don't like you change their structure. On the other hand, they don't want to increase the cost.
Do you apply the soil columns near the tunnels? Or you do some treatment of the layer?
There are different ways. The first thing is because vibrations coming from rail. The ideal way is with the source, you can place near the source. And then in the tunnel, there's so small space you can work. Here's a rail, here's a tunnel. The tunnel is a circle. It is only 15 centimeters for me to work. I said it's not possible to design it. So the other way is when it's transmitted on the way to the structure, to the buildings nearby, you can put something in the middle. But ideally, you start from the source, near the source, you can do it. So it's quite complicated to it. But for Peking University, they have very expensive equipment. So for them, the cost is not a problem because their research is more important. Yeah.
Actually, I got another idea from your presentation regarding the offsetting.
Offsetting.
Yeah, offsetting materials. Maybe we can explore another opportunity with the LIG next one. Maybe we can explore another opportunity regarding the development of the offsetting material. So for the out.
Yes, I'm collaborating with Fraunhofer Institute. You know Fraunhofer Institute, EMI. Timo used to work. It's the Institute for Impact and how do you call it? Impact and penetration. Or how do you call the name?
Exactly, the name is called Kurzzeit-Dynamik. It's a short time dynamics.
Short time dynamics. Yeah, high velocity. And they are developing the organic materials for the armor for protecting the organs of the soldiers. So they do lots of experiments.
To know what I'm thinking is actually we try to simulate the penetration of the projectile through the aluminum glass. But at the same time, if you do something, to invent some authentic structures to stop the penetration of projectile.
Actually, there are already like several publications that try to use authentic materials particularly for impacts resistant and energy absorption.
But then it's not.
So we can put that material to Korean missile.
Yeah. Yeah. I think what is most interesting is when you have very sensitive equipment to low frequencies. Or the,
Like a semiconductor.
or the people living nearby are complaining of the music, they are very sensitive, then the cost is not a problem.
Maybe I think you can apply semiconductor companies, but they are
Yes.
much.
Yes. Semiconductor companies, my colleague has an ongoing project for MEMS, where they really want to reduce all the vibrations which are sensitive to the MEMS and NEMS.
No, I'm serious.
Yeah, civil engineering is like the cost is they want cheap materials.
Sure.
When I put the the fiber reinforced concrete, I said that the cost for the concrete will increase by 50%. They cannot accept it. It's
Actually, obviously, they can pay. So if they can pay more,
They
they
can
are
pay
ready
more?
to pay more.
Really?
Yeah.
Oh,
Yes.
okay. Good
Sure.
using maybe in Korea.
Yeah, let's think about both the team. Okay, thank you very much for
Thank
your
you.
presentation.
Thank you.